Okay, so now we're going to talk about the Taylor series, and the Taylor series is one of the most important ways that we apply calculus to understanding functions and how they vary, and particularly in how we make an approximation to a function in a straightforward way that we don't know doesn't leave anything out, or we understand really well what it leaves out. So the Taylor series is really useful when we have a function that's difficult to evaluate and we'd like to evaluate it in a more simple way, or when we have an unknown function, but we can make experiments about pieces of its behavior and then build information from those to make more and more realistic approximations to what's going on in the real world, even without knowing what the underlying function is. We'll see a little bit about how that works, but for now we're going to do some, when we just do discussions in class and the homework problems, but for now we're just going to discuss the Taylor series and a few really straightforward applications. Okay, so like we said in the last video, the Taylor series notationally has, it's a function of x, it depends on x, but it also depends on a parameter a, which is like a value that x could take, or it's an expansion in the Taylor series, an expansion in the neighborhood of a. The first term is just a function that we want to approximate, evaluated at a. Then the second term is x minus a over 1 factorial, which is just 1, times the first derivative of f of x, which is the function as it depends on x, but after we take the derivative, we evaluate it at x equals a, and then the next term is x minus a squared over 2 factorial, and so on. This is the way you write it in a more condensed form. It's a little hard to read this. Here's the factorial down here with an exclamation point, which means n times n minus 1 times so on, so on, so on, all the way down to 1. Here's the nth derivative of the function, evaluated at a. And remember, take the derivative first with respect to x, then plug in the value for a. Don't do it the other way around. You'll get really confused. I do it all the time. It's not a problem. Just realize that that's something that's easy to mess up. Okay, let's do a couple of examples. How about we just take a simple quadratic function of x, and let's just take, I don't know, 4x squared plus 2x plus 1 as our function. Actually, I'm going to switch colors because that's not very clear, but I think you can read it. So here's our quadratic function of x. I want to take the Taylor series approximation to this quadratic function of x, and let's evaluate it at a equals 1. So Taylor series of x with a equals 1 of this function q of x. Okay, how do we do it? Well, the first thing we do is we evaluate q of x. We want to find the function evaluated at point a. So what's this if we evaluate it? X equals 1. X equals 1. X squared equals 1. 4 plus 2 plus 1. That's the first term. What can we notice about the first term? It doesn't depend on x. It's just a constant. If we were to plot this function, which we can quickly do, here's x, here's q of x. Let's figure out what we want to do. 4 plus 2 plus 1 is 6, 7. So this value at x equals 1 has the value 7. What does it have at x equals 0? It has the value 1. So it does something like this. And then it goes up like this. And what does it do on the other side? Well, it also goes up, but we need to figure out a little bit more. What is it at minus 1? This is 4 minus 2. So that's 2, 3. The value is 3 on this side. At minus 1, so not as high as 7. We're about like that. So it should, and where's the minimum of this function? How do we find the minimum of a function? We take its derivative, we set it equal to 0. So that's 8x. 8x plus 2, 0. So the first derivative of x, q of x, which we're going to need in a second anyway, is, let's see if I'm not running out of space, 8x plus 2. Where is that equal to 0? Because I want to find the minimum of this. I set that equal to 0. Move the 2 to the other side. X equals minus 2 over 8, or minus 1/4. Minus 1/4, so that's somewhere back here is the minimum. So we now have our function q of x something like this, with its minimum at minus 1/4. Minus 1/4. Okay? Everybody on board with that? Okay, so what's our first term in the Taylor series then? Our first term in the Taylor series is just a constant, and it's just the value of this quadratic function evaluated at x equals 1. So that would be 7. So the first Q0, call it, that's the approximation. It's just a straight line evaluated at that point. So what's the next term? Okay, the next term is what we just had over here. It's the first derivative of this, but first derivative then evaluated at a, and a in this case is 1. So the first derivative is 8x plus 8a, but a is going to be evaluated 1. So 8, reading parentheses here, plus derivative of this term, 2, plus 2, derivative of this term, 0. And then we multiply that times x minus 1 over 1 factorial, but 1 factorial is just 1, so we can forget about that. So now we've got 10 times x minus 1. And you might be thinking, how do we plot that? That's kind of a nasty thing. Well, we actually know what it's going to be because these two together will form the best linear approximation to this quadratic function that we can get based on being tangent at this point right there at x equals 1. So we can draw that line pretty quickly, and it'll be something like this. It's a straight line that is just touching the function right there, the tangent right at that x equals 1, x equals a equals 1 point. Okay, what's the next term in this series? The next term in this series is the second derivative of this. So the first derivative is 8x. Let's write it up here. First derivative x equals 8x plus 2. So the second derivative is, and I'm using primes. I could have also used a parentheses and a 1, a parentheses and a 2. I could have also written d by dx. All of those are equivalent notations for taking the derivatives of a function that depends on only one variable. 8. So now it's just a constant, 8. It doesn't depend on x, we don't need to evaluate it at a. Okay, what do we got here? Well, we do need to multiply by x minus 1 squared. What do we got here? We've got something, how it's a quadratic, just like this was a quadratic. Let's see, it's got a constant part, it's got a linear part and a constant part, and here, part that's linearly dependent on x is what I mean by that. It's got a quadratic part that depends on x squared over here, and then also there's a linear and a constant part hiding in here. What if we expand all of that out? What will we get? Let's erase the function, because we're going to know what's going to happen in just a second. All right, let's expand it out. We get 4 plus 2 plus 1, 7, plus 8 plus 2, 10x, 10 minus 10, plus 8 times x minus 1 squared. So let's do that part out. 8 times x minus 1 squared is x squared minus 2x plus 1. Everybody on board with that? Okay, here we go. Next one. Now we want to collect all the constant terms together. Or actually, let's collect the... Ha! And we've already made a mistake. Who caught the mistake? Maybe you already have seen it. I should have divided this by 2 factorial. 2 factorial is 2 times 1, which is just 2. Which means that I shouldn't have had 8 here. I should have had 4 here. Okay? Why did I know that was going to be the case? Because now, look, 4x squared up here, there's only one term that's got x squared on it, and it should be 4x squared. It's the same term as we found before. Plus, what's the next term? All right, let's collect all the linear terms. We've got 10x over here, and we've got 4 times minus 2x. 10 minus 8 is 2x. Same. Okay, now we're starting to see the pattern. 10, 7 minus 10 plus 4 is 1. We have the same polynomial coming back out of the Taylor series that we put in. It didn't look like it at first, but it was. And in fact, I could have expanded about any other a, not just x equals 1, and it would have worked out to be the same thing. That's because the power series, the series that we were talking about before, has a sense of uniqueness to it. So you can't confuse parts of a power series that go with the linear part with parts that go with the quadratic, with the squared part, with parts that go with the constant part. You can separate those out, and they always separate themselves piece by piece. Sometimes it takes a little algebra to do that, and sometimes it takes a little evaluation to do that. But in this case, we get that pretty straightforwardly. Okay, that's the first example of the Taylor series. Okay, in the magic of the quick erase, we can do one more example before we quit. What's the Taylor series approximation around x equals 0? Sometimes that's given a special name of the Maclaurin series when it's around a equals 0. For the function e to the x. E to the x may not be that familiar to you this moment, but it certainly will be by the end of this class. So e to the x has the great property that the derivative, d by dx, of e to the x is just e to the x. And that makes our job really easy in evaluating the Taylor series. Okay, so the first term in the Taylor series is e to the x evaluated at x equals 0. What's that? Well, e to the 0th power, or anything that's not infinite to the 0th power, is just 1. That's the first term. What's the next term? We need to take the first derivative of e to the x, which is just e to the x again, evaluated at this location, which is 1. E to the 0 again is 1. But what about this other stuff? We also have x minus 0 over 1 factorial. Well, that's just x. Because 1 factorial is equal to 1, and x minus 0 is equal to x. Okay, what about the next term? The next term is the second derivative of e to the x. So e to the x, the first derivative is e to the x. Second derivative is all still e to the x. Evaluated at x equals 0. That's still e to the 0. So that's 1. So we don't have any derivative part to take track of here, but we do have this x minus a squared over 2 factorial part to keep track of. What's that going to be? That's going to be x squared over 2 factorial. And I think you can see the pattern now. We can easily do the rest of these. X cubed over 3 factorial, x to the 4th over 4 factorial. Nice and easy. Okay. What does e to the x look like? Well, it grows exponentially like that. Does this term grow exponentially? No, it does not. That's just giving us the constant value of e to the x at x equals 0. Does 1 plus x grow exponentially? No, it does not. It's a linear function. So it has a little bit of tilt to it, but it's not fitting. It doesn't fit. It goes through this point, but it's a line, not an exponentially increasing function. What about this quadratic term? Well, now that's bending upwards, surely, but it doesn't fit this whole function. So the point is we're adding more and more things. We're getting closer and closer, and probably would have looked more like this. And then the next one would have been something like this, and so on. They're getting closer and closer to this function as you go to larger and larger values, but it takes all of them to get the whole function back.